Thanks for the introduction. And thank you all for showing up at this ungodly hour of 8:30 in the morning. I certainly struggled to get here today, but I'm happy to be here to tell you about our work on Crossroads, and this joint work between my mentee David and my advisor Srini at MIT. So as Roger was saying, our motivation starts with an attempt to whistleblow. Let's say we have an Alice who's a government employee, and she wants to whistleblow to journalist Bob that the government is spying on us. So she somehow wants to let the world know that this is happening. And in today's world, she might do this over an online messaging system, like an email or some sort of chat application. But as evidenced by this message that Alice is actually trying to send, it's very possible that there's an adversary sitting in between them, snooping in on their conversation. And this adversary might learn the fact that Alice is the one leaking this information, and this might get both Alice and Bob into some serious trouble. There's a lot of historical examples of this actually happening, and at least certainly U.S. history. What can Alice and Bob do? They could use end-to-end encryption or encrypted chat applications like Signal to prevent the adversary from learning what they're saying. But encryption still leaks a lot of sensitive information in the form of what's called metadata. And these metadata include things like the identities of the participants, so the fact that Alice and Bob are talking to each other, the timing of their conversation, so when and how often they're talking, and also the sizes of their messages. So are they sending small or large messages? These sort of metadata are not protected by your standard encryption. But sometimes they could be just as sensitive as the actual content of the messages. So for example, just the fact that there's a government employee talking to a journalist at an untimely manner, it could actually get them into trouble, even if the adversary never learns what's actually being said. So our goal in Crossroads was to design a messaging system with strong metadata privacy. Now what this means is that even if the adversary is snooping in on the conversations or the communications in this network, it shouldn't learn anything about the communication patterns of the users. So for example, with 3 users, based on the adversary's observation, these 4 scenarios should look indistinguishable. So it shouldn't be able to learn which pair of users are actually communicating, if any pair is communicating at all. And in general, we wanted to guarantee with cryptographic proof that the adversary learns nothing about all of our honest users' communication patterns. So the adversary should get no information by observing our system. And we specifically focused on one-to-one messaging. So these are messages exchanged between 2 individuals, not like a group messaging setting where there's multiple users talking to each other simultaneously. So in a concrete deployment, we're considering a scenario where we have a large number of users and a smaller number of servers in the order of hundreds to thousands of servers that are routing these users' messages. And we assume an adversary that has a global view of the entire network. And it could also control a fraction of the servers that are actually routing the users' messages, and a large number of malicious users as well. So Crossroads is designed specifically to prevent any sort of metadata leakage against this powerful adversary. So before I dive into how Crossroads actually works, I first want to review quickly of a building block of Crossroads called mixnets. So in a mixnet, the servers are laid out in series, and users can send messages through these servers in a way that doesn't reveal who sent which message. So to do that, users employ a technique called onion encryption. So what that means is they encrypt the messages for all the servers, but in kind of reverse order. So first you encrypt it for the last server using this yellow key, followed by the middle server, and then followed by the first server here. And then the first server collects these messages and starts processing them. And it does so by randomly shuffling the messages, and then decrypting a layer of encryption, and then sending it to the next server. The second server does the same, so it shuffles and decrypts a layer of encryption and forwards. And lastly, the last server decrypts and releases a shuffled version of the plain text messages here. So an important property of these mixnets is that this output now is a random permutation of all the inputs here. And specifically, this permutation that's used to shuffle these messages remains unknown to any single server or any network adversary that's monitoring the communication between the servers. So as a result, the adversary shouldn't be able to tell who sent which message because it's been randomly shuffled. The ordering has been randomized. And in fact, this property holds true as long as there exists one honest server in this network that's randomly permuting the messages. So all we require for privacy of mixed nets is existence of one honest server. So in Crossroads, we use these as building blocks, and we lay out many of these mixed nets in parallel, each of which will handle a fraction of the user's messages. And these mixed nets, or these chains, are constructed in such a way that every chain contains at least one honest user. At a high level, this is done by making the chain long enough so that this happens with overwhelming probability. So in any case, we have these secure mixed nets with one honest server laid out in parallel. And of course, we have our users as well. In addition to that, we also have mailboxes, each of which corresponds to a user. So you can think of these mailboxes as an email address with email inbox, where users' messages are deposited, and they can download them at some point. So to actually send a message, each user sends a message to L different chains, where this value of L and the choices of the chains are chosen in such a way that every pair of users intersect. So for example, it might look something like this. When L is equal to 2, you can see that every user here is sending a message to 2 different chains, and every pair of users meet at least one chain. So for instance, the first 2 users here are meeting at the first chain on the top. So once the users send these messages, these mixed nets process the messages kind of independently and in parallel. And finally, the last server of each mixed net is going to forward the messages to the correct mailboxes. So at a high level, this is how our system works. And to tell you a little bit more detail about it, I'm going to focus specifically on one of the chains and the users that chose this chain to route their messages. And because these mixed nets are operating independently and in parallel, so there's no inter-mixed net communication, what I'm about to describe is just replicated across all the mixed nets that we have. So within the mixed net, there are 2 sets of users that we have to consider. The first are the group of users who are actually in a conversation. So for example, let's say user A and B here are talking to each other. In this case, we assume they share a cryptographic key with each other. And the second class of users are those users that are not communicating with anyone. So for example, user C here. And in this case, they just generate a random cryptographic key that only it knows. And each time epoch of communication, every user sends one message. And these messages are tuples of the form destination mailbox followed by a ciphertext. And if you are in a communication, then you send messages to each other's mailbox. So for example, user A is going to send message to B's mailbox, and B is going to send message to A's mailbox. And the ciphertext in this case is encrypted using the shared cryptographic key. And if you're not talking to anybody, like user C, you just send a message back to your own mailbox, encrypted under this randomly generated key. So these messages are now shuffled through the mixed net. And at the end, every mailbox is going to receive one message. But what you might have noticed is that user A and user B's messages have been swapped. So now, user A can just go download the message in its own mailbox and decrypt it using this shared cryptographic key to learn what message B has sent her. And B can do the same to get the message that A sent him as well. So this is how users exchange messages and how they talk to each other in Crossroads. And this simple design is actually sufficient to provide metadata privacy within each of these chains. At a high level, the security argument is pretty straightforward. So first thing to note is that the number of messages is fixed regardless of whether you're actually in a conversation. So everybody sends and receives one message. And these mixed nets hide the origin of every message. And specifically what they hide is whether 2 messages have been swapped, in the case of conversation, like the left diagram, or have not been swapped, in the case of no conversation, like the right diagram. And this sort of pairwise indistinguishability generalizes to arbitrary number of pairs within this mixed chain. So within a mixed net, we get this perfect metadata privacy. But of course, we have many of these mixed nets, and we want to provide a more global notion of metadata privacy as well. And for that, we leverage the fact that we have every pair of users that intersect at one of these chains. So what this means is that at any given point, any user could be talking to any other user, because they're all intersecting. So as a result, the adversary can't tell who's actually talking or if anybody's talking at all. So more detailed versions of our security arguments are in the paper, but we specifically rely on the fact that these mixed nets are correctly hiding who sent which message. And I mentioned before that we only need one honest server to exist in these chains to ensure this property. But as it turns out, in real life is not that great. That's not a true statement. And this is due to what's called active attacks. So in an active attack, a server may deviate from the protocol in order to break privacy. And for example, let's say we have the first server who's malicious, and it wants to figure out if user A is talking to someone. To do that, it's going to just drop the message A sends and replace it with a dummy message that goes back to A's own mailbox. And so now this message gets processed by the mixed net, and at the end, the adversary is going to observe that A's mailbox now has two messages, one from the conversation partner and one dummy message that it inserted. It's also going to notice that now user B's mailbox has no messages, and this is because it dropped user A's message. So now just by counting the number of messages in each mailbox, the adversary can figure out that A and B are in a conversation with each other. So one of the goals of Crossroads was also to protect against these sort of active attacks as well as all the passive attacks. And for that, we turned to zero-knowledge proofs. I won't have time to dive into how these proofs actually work, but at a very high level, these proofs allow servers to prove that they didn't launch any active attacks and they correctly shuffle these messages. And they allow other servers to verify this claim in a way that doesn't reveal any privacy. And traditionally, this has been done through a technique called verifiable shuffle. And to prove that you've correctly shuffled m messages, it requires m log m exponentiations. And to verify such claim, it takes 4m exponentiations. And these exponentiations are fairly expensive. So as a result, verifiable shuffles have been pretty high overhead way to protect against active attacks in the past. So in our system, we developed a new primitive called aggregate hybrid shuffle that's designed specifically for messaging. But we can bring down the cost for proving down to just m plus 2 exponentiations and cost of verification down to just 4 exponentiations. So we reduce significantly the amount of expensive cryptographic operations that need to happen. And as a result, we can introduce verifiability and protection against active attacks with much lower overhead than traditional verifiable shuffles. And so with this new technique, we can actually perfectly protect against active attacks in our system. And so within each chain, we get this local metadata privacy that I've mentioned before. But of course, we wanted a global metadata privacy. And again, for that, we needed every pair of users to intersect at one of these chains. So, and we want to do this in a way that every user is sending a fixed number of messages L to L different chains. And we somehow want to evenly distribute this load across all the chains in a way that also minimizes L. So for example, if every user sent messages to every chain, that would actually be a secure design of Crossroads. But of course, it wouldn't scale because the point of each of these parallel mixed nets was so that they only handle a fraction of the user's messages, not all of them. So in Crossroads, we have an algorithm that allows us to achieve L equals square root of 2n. And actually, in the paper, we show that there's a lower bound on L. It has to be at least square root of n for Crossroads to remain secure. So what we concretely have, our concrete protocol, you can think of as a square root 2 approximation of an optimal version of Crossroads per se. And this actually has significant impact on the scalability of our system. So for example, let's say we had n chains and m users, each of which is sending square root of n messages that are evenly distributed across all the chains. Then every chain is going to handle m over square root of n messages. So one nice property about this is that if we increase the number of chains, which is directly correlated to the number of servers in our system, the load per chain goes down. So what this means is if we wanted to scale to larger numbers of users, or we want to improve the performance, then we can just simply add more servers to our system and add more of these parallel mixed nets to achieve that goal. So this has a nice property that it scales horizontally. But you might also notice that this is not quite ideal, in that an ideal scaling would scale something like m over n instead. So we are the square root of n factor worse. And in fact, a lot of previous work, at least in theory, do scale in this ideal way. But as we'll show in the next few slides, because of the constants hidden in this big O between our system and previous system are so different, we can still outperform a lot of previous works in a lot of reasonable deployment scenarios that we've considered. So to actually test our system and compare against prior works, we implemented a prototype in Go. And we tested on up to 200 Amazon EC2 servers using 256-byte messages. So these are your standard text or SMS messages. And the network was configured to handle up to 20% malicious servers. And we compare against 4 prior works that provide metadata privacy. And just to summarize them quickly, Atom has the same threat model and essentially the same privacy guarantee as Crossroads. Pung provides the same privacy guarantee, but against a stronger threat model. So in Pung, actually, the adversary could compromise all the servers, not just a fraction of the servers. And Stadium and Karaoke have the same threat model as Crossroads, but provide a weaker notion of privacy called differential privacy rather than cryptographic privacy that we can provide. So it's not quite apples to apple comparison, but these are kind of the closest things that we have that came before us. So first thing we wanted to see is how all these systems and ours scale with the number of users. So we fixed the number of servers at 100 and varied the users from 1 to 8 million. And what we found is that expectedly our system scales linearly in the number of users, or as latency increases linearly in number of users. So to highlight a number, at 2 million users, it takes about 220 seconds or a little under 4 minutes right now. So when you compare against previous differentially private works like Karaoke, there is a fairly significant performance gap still. So you can think of this gap as the current gap between differentially private communication systems and cryptographically private communication systems. So you're paying for the strong level of security. And when compared to previous cryptographic works, though, we provide actually significant latency improvement. So for example, when compared to Pung, at 2 million users, Crossroads is about 4 times faster. And in fact, because Pung scales quadratically in the number of users, this gap increases to 8x for 4 million users, and it would increase to 16x at 8 million users, and so on. So this trend would continue indefinitely. So at least compared to prior strongly cryptographically secure systems, Crossroads scales better in the number of users. And we also wanted to see how Crossroads scales with more servers. So we fixed the number of users at 2 million and varied the servers from 50 to 200. And what we found is the kind of the expected scaling that if we add more servers, the latency decreases. It's a little bit difficult to see here what exactly the scaling pattern is, but our latency is decreasing as this 1 over square root of n that we mentioned before. And all the other systems here are actually scaling more like this ideal scaling of 1 over n. So what that means is that with enough servers, Atom and Pung would catch up to the performance of Crossroads eventually. But based on our estimation that was used, based on this graph and our extrapolation of this graph, we expect it would take close to 1,000 servers for Pung and Atom to catch up to the performance of Crossroads at 2 million users. And because, again, Pung scales quadratically in the number of users, it would take even more number of servers to actually catch up to Crossroads at 8 million or 16 million users in the future. So again, we think that we scale better in a lot of than previous works that provide cryptographic privacy in a lot of reasonable deployment scenarios that one might consider. So in conclusion, I told you about Crossroads, which is a messaging system with cryptographic metadata privacy. And we have this new primitive called aggregate hybrid shuffle that can efficiently defend against active attacks. And we can support 2 million users in a little under 4 minutes. And there's a lot of aspects of the system not covered here, including our limitations in the paper. So please check it out. And the code is available at this address. Thanks for listening this early morning. And I'll be happy to take any questions. Yeah.
Hi. I just want to ask, there was a recent work named Yodel in SOSP.
That's right.
Can you comment on the difference?
Yes. So Yodel is, first of all, still a differentially private system. So what Yodel does is actually they take Karaoke, and Karaoke's so Yodel is a system that can do sub-second latency in a similar deployment setting. So how are they doing this so fast? Well, actually, what they're doing is they're using Karaoke as a way to establish a fast circuit through the network. So they pay like a 10-second or 20-second penalty to establish a fast circuit, like similar to Tor, actually, if you know how that works. And then they use that circuit to do this fast communication. And actually, Crossroads can benefit from that sort of paradigm as well. So we can establish a slow one time, 4 minutes to establish a circuit, and then the rest of the operations could actually be done fairly fast as well. But the main difference still is that Yodel is still a differentially private system, while this is a cryptographically private system.
Actually, I got very curious while listening to the talk.
Yeah.
I have a quick question. Can you comment on the users arriving and departing, and how does your system maintain these properties?
So that's an excellent question. So user churn is a serious concern potentially. So in our system, what we actually have users do is they kind of submit 2 messages at a time, one for the current round and one for the next round. So in case they go offline, the server is now taken these pre-submitted message, and this message actually is always of the form that either indicates they've gone offline to their conversation partner, or it's a loopback message that goes back to your own mailbox, in which case nobody cares anyway that you dropped off. So that way users can know that the conversation partner dropped off kind of unexpectedly and stop talking to that person correspondingly. So.
Thank the speaker once again.